today discuss about the Newton's law of motion and we see the applications of the first law applications of first law and third law. Basically, there is use of real law of motion. So I am telling that second law is basically real law of motion, and I'm telling that there is one law of motion not given by the Newton. I think atomic founder Rishi Khanna is from the India, Gujarat, basically propounded laws of motion. And second law is why real law. I am giving two proofs. Proof number one. In this case, you know, force is equal to dp upon dt. This force is external, and external force it is zero. Then dp upon dt telling that dp is equal to 0. It means here momentum is basically constant. Again, I am telling that there is mass in the momentum, and you can write dv upon dt. This is equal to 0. It means dv is equal to also what? 0. It means velocities is constant. So when change in momentum is 0, Change in velocity is zero. It means momentum is also conserved. Velocity is also conserved. This is telling about the conservation of velocity and momentum tells that this is proof of first law. Proof of first law of motion. Of motion. Again, from this second law, we get third law also. So first law tells what? There is no external force. Body remains at rest. And if body moves, then momentum remains what? Conserved. Velocity remains what? Conserved. Now, I am closing from the second law. Third law also. So what about the third law? There is force when two body come in the interaction. Two body interact together. So there is force on second body, force on second body by one. Again, in the opposite direction, force on one by the body two. So I write here force on two by one is equal to d p2 upon dt. If force applied on the second body, momentum change of second body. Again, if it is force on 1 by 2, this is equal to dp1 upon dt. So what is sum of these forces? Sum of these forces are F21 plus F12. This is equal to dp1 upon dt plus dp2 upon dt. So this is equal to d upon dt is common here. You can say second momentum and first momentum sum. This this is what? External force. External forces are zero. Total external force this one is there. And total force is what? External is F21 plus F12. This becomes zero. So what happened here? Again, this P1 and P2 becomes what? Zero. This force external, if external force is zero, then d upon dt into P1 plus P2 total momentum also becomes what? Zero. In this case, you can write here that total force is what? F21 plus F12 is equal to 0. You can write here F21 plus is equal to minus of F12. This means this is a force of action equal and opposite to force of reaction. This is the third law you are getting in this part and in the this part. So you can imagine that there is one law of the motion, not three law. So Rishi Kanal of Gujarat. Rishi means word research is obtained from the Oxford Dictionary. So research word is copied from the Sanskrit word. In the previous class, we discussed about the third law of motion, and today I discussed about the basically there is one law of motion. So about the forces, about the tension, we discussed in the previous classes. I am applying some applications in your life, in my life. So when a person is walking, you are walking on the surface, on the ground. What happens here? So when human is walking, one of the leg remain horizontal, yeah, vertical, you can say. Some part of this leg go to back. This is what force of action is applied while the motion. Force of action. This is what from the ground there is reaction force. Force of reaction. You can also indicate by the arm also. So this is making what? Making certain angle from the ground. And this component becomes what? For the R force, reaction force, this component in x-axis on the ground, this is R cos theta. And again, its component in the y-axis. In the y-axis, this is R sin theta. So this force applied for the horizontal motion, horizontal motion, you are moving in the forward direction, and this force R sin theta in the y-axis, it is applied on the body and it balances the weight of the body. R sin theta is equal to mg. r cos theta. So in the vertical direction, mg of the body act here, mg of the body act here. There is mg, there is again r cos theta, there is again r sin theta. You know there is mg. So r cos sin theta, r sin theta here, balance the weight, is equal to what? Mg. Direction may be different. You can also write minus mg. So r plus r sin theta plus mg is equal to what? 0. So you can say net force in the vertical direction. Net force in the vertical direction is what? 0 here. So horizontal motion takes place by the r sin cos theta, and the r sin theta balances the weight, and there is no net force to move upward and fall down of the body. So this is the fundamental applications. Second application I discuss here, horse and cart problems. Horse and cart, we find out the acceleration because we have idea of the tension. In the previous class, I discussed also about the exact on the tension, on the molecules, on the atoms, on the string. I discussed. So there is a card. It has wheels here. Its mass is greater and connected with a horse. Horse bearing the head. There is legs. 4 legs, you know, in the horse. This horse has mass m, a small m. So in this horse, leg also apply what? Leg apply what? Force of friction. Like the human. Walking of the human, running of the human. Horse also run, apply force by the legs on the ground. Again, there is what? Force of reaction. Force of reaction. Making how much angle from the horizontal from this R. Angle is what? Making theta. This is R cos theta in the horizontal direction. In the x-axis, in the y-axis, there is R cos theta. So motion is by the horizontal force R cos theta. After the reaction force acting by the ground, by the road, you can say. And acceleration is due to applied the force. If I apply force on the car moves in the forward direction. If apply a force on the fan, wing, so fan also rotates. So this gives the same acceleration of the acceleration of this horse, acceleration of this car is what common, same by the force applied horizontal direction r cos theta. So both have same acceleration, and this force is action in the horizontal. So one tension acts in the this direction. You can say minus t if you calculate by the x and y axis. X is positive, here x is negative. So this is positive r cos theta, and this is tension minus t. Direction is different. So I am writing here minus t. Again, on this force, remove the force. In this force, one force is r cos theta, other force is what? Minus t, tension. Third force is r cos theta, and in the downward direction, mg is acting, which balances the weight. So free body diagram. Remove the horse. Remove the one body. Huh? On that body, how much force is acting? So force has one force, second force, third force, fourth force. As the free body diagram. Again, for the horse, you see there is four forces in the horizontal direction. In the horizontal direction or x-axis for the motion. Force is what? R cos theta minus tension is equal to what? Net force. So net force is how much? Mass into acceleration. So I am writing here R cos theta minus tension is equal to m into a. Is acting here. I consider this is equation 1. See the vertical direction. In the vertical, mg is balanced by the r cos theta. So in the horse vertical direction or in the y-axis, how much forces are acting? Suppose r cos theta is positive in the y-axis. So mg is suppose negative. So I am writing here mc is equal to no net force acting. Horse is not going down, horse is not going up. So F net is what? basically 0. It is equal to basically 0. So what we had, r cos theta minus mg is equal to 0. It means r cos theta is equal to mg. This balances the weight. I am not considering any equation in this case. Sirf I am observing the free body diagram. Keep the horse out of the system. It is our choice. Now come to the card. For the card, again consider in the horizontal direction along the x-axis. So tension here in this direction. Again, you know, tension also act in the positive direction. So this is what plus t. Acceleration of horse and cart is same. Horse move faster, then acceleration will be fast of the cart. Horse is moving with a small speed. Acceleration of the cart is also small. So here is tension acting in the forward direction in the horizontal, but there is wheel. There is what friction force in the backward direction. This is what friction force. F, small f. So acceleration is forward, tension is forward, and friction is opposing the motion of the cart. So I am writing here T positive minus friction is equal to net force in the horizontal direction. Again, P minus friction is equal to net force is mass into acceleration. Here mass of the cart is more. I am writing capital M. Acceleration of the horse and cart is what? Same. So I consider this is equation 2 in the horizontal direction. Come to the vertical. In this cart also there is what? mg in downward direction in the negative y-axis. Again, if their surface is at right angle, so there is what? Opposite to mg, there is normal reaction force. Normal reaction force. You can write n, you can write r in the as the book writes. So it is making how much angle? It is making basically 90-degree angle from the horizontal, from the surface. So here in the vertical direction in the y-axis, you can say there is mg minus normal reaction is equal to net force. So this cart is moving horizontal, not vertical, not downward. So here mg minus n is equal to what? Net force is not exact, so it is what? 0. You can say mg and normal reaction is equal. So there is no net force. Equal forces, but direction is opposite. So we have to find out what acceleration. You have two equations in the horizontal to find out acceleration. So I am adding here equation 1 and equation 2. 1 is how much? I remember this is r cos theta minus t is equal to m into O for the horse, again t minus f is equal to capital mass into a for the card. To add it here, r cos theta minus t plus t minus f is equal to capital M small m at a acceleration is equal. So plus t minus t go to the house. Acceleration is equal to how much? This is equal to r cos theta minus f upon total mass. This gives the acceleration. You can also write here horizontal force minus friction force upon total mass is what? Acceleration. This you can also write. Again, we see the application in the form of language. If I write in the box, then this is what? A formula. Third application I am writing here. Operant weight. Measurement of operant weight. When you can measure, when you are moving up or down and at the wrist, and when acceleration due to earth work. So there is four cases we have to find out, apply out. So a man in lift or elevator. You are in the elevator or lift. So elevator is where usually in the railway stations, airports, and lift is everywhere in the market. So first case is here, lift or elevator go upward motion. So in this case there is lift or elevator. Here you are standing and There is mg act here. You apply force mg on the earth towards center and at right angle from the surface. There is what? Normal reaction. You can write N or R, reaction force. If it is going upward, it means there is acceleration is in the upward direction of the lift. It means upward force is larger than mg. Our force, your force is mg, but normal direction is more. So lift go upward. It means I am writing here N minus mg is equal to what? Net force. This is very important to know. Again, N minus mg is equal to mass of my body into acceleration in the upward direction. Again, N is what? Apparent weight. This is equal to mass is common A minus Z. It means this is the formula for lift going upwards. This is what? Apparent weight N, mass of my body, acceleration upward minus acceleration of the earth. Again, when lift move downward, downward motion of the lift. Again, there is a lift chamber. A person is here applying force mg. There is normal reaction. If lift is going downward from the acceleration, it means there is what? Mg is greater than the normal reaction. Mg is more than applied force in the upward direction. So I am right here. Mg minus n is equal to net force downward. This is equal to mg minus n is equal to ma acceleration down direction. You can write here apparent weight. This is equal to how much? This is equal to m is common a minus g a minus g. N is right side, g minus a. This is again apparent weight. N go right, it's come here, so g minus a. If lift is at rest, no motion here. So what happens? In this case, there is no acceleration. There is no motion. It means acceleration is what? Zero. No net acceleration is here. No net force is here. So I am consider mg is equal to minus normal reaction. Action is equal to reaction. So you can say net weight is here. Also you can add it. Net force is what? 0 mg plus n is equal to what? 0. So body remains what? At the rest. Mass into acceleration you can also write. So mass into 0 acceleration. That is also a system to apply. Again, I observe fourth case. You can say this is a condition of free fall. Free fall. Fourth condition is free fall of the body. You know the normal situation. If there is mg, there is what? Normal reaction. So for the downward direction, we know apparent weight is equal to m into g minus a for the downward fall. So free fall means what? Downward acceleration is equal to g, acceleration of the earth towards the center of the earth. So if there is m or g minus c, so there is no apparent weight. Apparent weight is 0. Apparent weight is 0. So people feel that, public feel that, person feel that there is no weight of the body. So weightless feeling during fall of a person, of a body. This is the application in the elevator or in the lift. Again, we observe here in the language application, elevator weighing 400,000 kg moving upward from the rest and on the cable 48,000 Newton force is applied. How much distance it reaches during motion? This is problem by the words you can see. So everything given here, I told you that there is mass of the lift is 4,000 kg. So upward force here mg of the lift is 4,000 into 9.8 meter per second is equal to 39,200 Newton. Force is applied. And upward force applied for the motion. This is 48,000 Newton. So you can make a diagram, simple diagram to see that center of the elevator. There is mg. Mg value known. This is 39,200 Newton. And upward direction force is here on the cable is 48,000 Newton. So acceleration is in this direction, you know. So I'm writing here F minus mg is equal to net force in upward direction. So how much F 48,000 minus 39,200. This is equal to what? Net force acting on upward direction. So F net is how much? F net is here. This is direction of the mg. You can see the diagram. This is the upward force. F is acting. So this is larger than mg and going body upward. How much there? Zero. This is 8. This is 8. $48,000 39,200 00. This is 8. This is 17 minus 9. This is also 8. This Newton force effect here. So what is the acceleration here? Acceleration is you can find net force upon mass. Mass you have, time is given here, so you can find the distance. If net is 8800 upon 4000, this gives 22. This is 20. So almost 2.2 meter per second square. For the distance, you can apply S is equal to ut plus half at square. This is 0, half 2.2 into 3 seconds is time given. So this is equal to in the meter. In the next class, discuss application based on linear momentum and tensor. Thank you very much.